Welcome, everyone, and thank you for joining us this afternoon. I'm Andrea, and I will be your host for today's session. I'm glad to welcome today Philippe, who is a security researcher at Quarkslab, where he had been working for the past few years on car security. His research interest lies in embedded devices and software-defined radio, and these are the things that we will touch upon today, in addition to answering the question why and how we could build a car in a box. Philippe, now I would like to invite you to start your presentation.
Thank you, Andrea. Welcome, everyone. I'm very pleased that you joined this webinar. Today, we will talk about car hacking and how we work at Quarkslab to improve our car hacking trainings by building the project Car in a Box. First of all, before speaking about how Car in a Box was built and what we intend to do with it, I will speak a little bit about automotive and cybersecurity to give you the whole picture of why cybersecurity is important in the automotive world. First of all, what is a car? It's the same thing that has many decades. If you ask someone to describe your car, it's 4 wheels, a motor, but now it's become much more complicated because there is a lot of new improvement. For the last decade, we saw that there is a driving assistance with anti-collision system, line detection, with onboard camera that analyze the whole environment or radar. You have the active ESP and ABS for braking and handling the car, and also self-parking features. But new car also have a lot of connectivity. 2007, if you have Bluetooth in your car, it was a high-end car. Now it's just a mandatory feature to link your phone, read your SMS, or have a call while driving. You also have GPS and 4G, 5G connection for equal and other traffic assistance. And some cars also have a Wi-Fi hotspot on board. But while talking about onboard system, you have also onboard services. Now modern cars have mobile application, whom you can control your car at distance to start or stop it, or for example, initiate the heater in winter to have a hot car when you get in. You have localization, auto diagnostic system, and many others. And the most important things we speak about is the autonomous driving. When we speak about autonomous driving, we will think about Tesla, but for your information, Mercedes reached the level 3 of 5 fall 2021 for autonomous driving, which means the car is able to drive on a specific road at a specific speed by itself. That's very, very important. But how can we get such feature and intelligence into a car? It's due to the ECU. ECU stands for Electronic Control Unit. It's like the picture you have on the right. It's a PCB with one or multiple microcontroller or system on chip. Their main role is to read data from sensor, then from this data, manage actuator to control the door lock or the steering wheel and many other things. And to be as efficient and as intelligent as they are, these ECU needs to communicate between each other or to communicate with other device or a backend through some different networks who can be wired or wireless. And as now in a modern car, you have between 50 to 100 of ECU inside. And as I said, there is many networks in a car. The most common and the most known one is the CAN, the Control Area Network. It was built in 1986, and it's still very, very common in car. Most of the important systems are use the CAN bus to exchange data for the powertrain control module or door lock system. But as the feature of a new car evolves, we need more bandwidth, we need more speed, and there is new network that were design, like Ethernet Automotive or FlexRay for drive-by-wire system, and for high quality multimedia content like audio or video, they design the most systems. And if we look at a car, what do we have? We have multiple embedded device which communicates through different networks. And all this evolution come very quickly into car, much more quickly than the automotive manufacturer and tier one manufacturer were able to integrate security into it. And then this led us to a very, very broad attack surfaces. In 10 years ago, the main attack surface you had on a car was the OBD2 port, the plug. You know, this is this plug you have near the driving wheel for diagnostic use. But right now, most of the attack surface are wireless. You have, as I said, Bluetooth connection, 4G, 5G connection, Wi-Fi. For autonomous driving or advanced driving, you have all the V2 vehicle ground infrastructure communication, which where the vehicle can communicate between each others or between their environment. You also have attack surface through the mobile phone regarding RFID or UHF or standard 4G communication. And all the electrical vehicles are growing in numbers. You also have now the power line communication as an attack surface. When you plug your car into the power charge, it will communicate with the grid to see how it can efficiently get energy with the grid. So you have also this kind of communication. And you have computer vision for obstacle avoidance and many other things, or thermal imaging. And with all these features, this leads us to a major milestone. So as I said before, there is many new features and improvements that were implemented into a car, but the cybersecurity was not their main was not an aspect of the production. So in 2015, two researchers, Chris Miller and Barbhack, did a very important things. On a Jeep vehicle, there was an infotainment unit, you know, the unit you use to listen to music and so on. It has connectivity through the one-star systems and over-the-air update. But those updates were not secure at all. So they managed to get a firmware, patch it with a backdoor from us, and through an exposed port, update an exposed services. Sorry, they update the firmware and they have control over the whole car. There was no segregation between CAN bus. So with the infotainment CAN bus, they managed to have control over the braking system or powertrain control module, and were able to accelerate or brake or turn the wheel while the vehicle was running and without any control from the driver. And this milestone was very important because it shows to the different manufacturers how it is important to integrate cybersecurity into the vehicle manufacturing. This is well, their proof of concept get to the recall of 1.5 million of vehicles in the US, which is very important. As we saw, new features were evolving very quickly into vehicle, but regulation were quite slower. There is a major regulation in 2020 from the United Nations Work Group 29, which integrated cybersecurity into the regulation. Now, new car from 2022 must have secure over-the-air secure firmware update integrated, and during the whole life cycle of the vehicle, cybersecurity has to be managed and integrated to the development. But with those, there is a great difference between security and safety. To remind you, safety is to avoid you being harmed by something exterior. You know, you're driving at the road, there is eyes on the road, so you have to keep control of your vehicle. That's where ESP get in action, and this is safety. And security is to avoid that an attacker or something malicious harm yourself or get information from you that you don't want to let out. And there is also regulation about safety, like the ECUS since 2015, 2056. The ECUS is now mandatory into new cars. That means every new car produced, manufacturer have GNSS connectivity. They can read GNSS data, but they also have data, voice call, and communication. So they have 4 or 5G on board every new vehicle, all of it. For example, in 2029, there was also the TPMS. It's a tire pressure monitoring systems that alert you when you have a flat tire. And this is also mandatory. And for a direct system, that means you have a UHF connection between every of your tires and one of your ECU. And there are proof of concept that you can manage, you can craft malicious signals to get rid of, to have action on some issue. So we saw that cybersecurity into automotive is very important because we need safety, but bringing safety into car also bring needs in security. And if we get back to what a car is, as I said, it's different embedded device, all the ECU, and different network that communicate, that allow ECU to communicate between each other. And we are clearly in our in Quarkslab domain of competence, So it's been years. Now we are doing security assessment on ECU and cars. We are doing hardware and software assessments, but we also find very important to train to get people working into car, different actor, so they will be sensibilized to the importance of having secure systems. And that's why we develop many car hacking trainings. And creating a car hacking training is not as easy as it seems. Why? Because you have to work on different network. You have to work and teach how a CAN bus works, but not only CAN bus, because there is many other things. And for each network, you have different protocol. You have CAN, you have upper protocol like UDS, ISO-TP, or specific Ethernet protocol like DoIP, some IP. So very, very large range of things to get in. A car is also a hardware system with many hardware embedded system in it, and each system has software. So you have to get on every kind of issues or vulnerability you can have, both in software or hardware or relation for both of them. And you have also front and back end application like the infotainment system and the back end, like I said, API, to control your car with your mobile. And each ECU has its own architecture. So when you are working on a car, you will have some kind of OS, like for the infotainment, the JNEV or QNX OS. Some other OS we have will work on an hypervisor, but most of the ECU will be just a microcontroller. So they will be running a specific firmware for their own architecture. And ECU architecture are not the most common you will find in other embedded devices. You will have Tricore or Renesas architecture, which are not always well documented. So as you see, creating a car hacking training is quite complicated because you have to get in all of those aspects. That's why we decide to get it easy at first, and we built an open source solution, which were the TinyECU. TinyECU is based on a TinyECU microcontroller. You can see on the bottom left of the picture. And it interacts with different sensors and actuators, like a real ECU. And it simulates 4 different ECU. It was quite basic and very good to attendees to get a fresh start into car hacking and how CAN bus worked. But this solution was not perfect if you want to get the whole picture. So This is a little bit of teaser for the next incoming training. We designed the connected TinyECU. It was a major improvement of the TinyECU. You have two CAN bus, you have different microcontroller which manage a modern protocol like some IP, DWIP, traditional protocol like UDS, CAN, and so on. You have an onboard backend API to simulate exchange with a mobile phone and to demonstrate some common vulnerabilities. It has its own key fob to have passive keyless and remote keyless entry capabilities, where there is also a lot of vulnerabilities to demonstrate. And it integrates a real ECU, so you have a lot of possibility with it. However, even doing such design is not as real as you can have if you use a real car. So the main idea when we did our training was to bring a car to the training. But it is not as perfect as it seems. Why? Because first of all, you cannot do such things everywhere. There is some place you will do your training without any garage and so on. So you cannot park the car, and well, without the car, you can have the real things. Then it alters the pace of the training. You know, you're in the conference room, you're doing your labs and so on, you're teaching stuff, and then everyone has to pack his laptop to go down 2 floors downstairs, get to the car, you have to prepare the car, and then attendees can start playing with the car. But even when they start playing with the car, you can fit 1, 2, 3, 4 people into the car who really see what's happening, and all the other ones are waiting, and it's not quite good. It's not as good as it has to be for the attendees. And when you do such things, you have to get access to a car, you know, because if you want to show tricks, you have to master it. And when you play on a real car, you still have the risk to break it. For example, every car have what we call a crash frame. So if you fuse a CAN bus and you trigger the CAN frame, the power control module will get in safety, and you won't start your car again unless you have access to a manufacturer diagnostic tool. So having a car training is not the perfect solution. And that's why we decided to work on the Car in a Box project. The idea is to get a car which is portable, which can travel with in train, in car, by plane to get to our training worldwide. And we get to this. I present you the Car in a Box. So it's a rugged case which respects the dimension to get into a plane. It has 16 ECU inside, the most important one for all the feature, all the main aspect we want to demonstrate on a car. It has 4 CAN networks, many LIN networks. LIN is a chip networks, very common in car. We have a full infotainment system, which is very important, Bluetooth and 3G connectivity. We have a command and control panel, which can be connected through IP to have a remote control. And this panel is important also because it shows the real state of the car. So when you start attending command of using the different buses, you can compare the effect you have on, for example, the instrument panel cluster and the real state of the car. And how did we build that? That's the main, one of the important things. First of all, you have to gather parts. You have to collect ECU. The first idea you can have is to go online on some different websites and to get used ECU. But doing such thing is not the best solution. Why? Because some ECU are what we call enrolled. They share information between them. If they don't have the same information, they won't start. They won't work correctly. It's to avoid some thief or things like that, or to avoid that people reduce the value of the odometer and they can resell their car with less kilometer than they really have. Then you will need to work properly. You will need to have access to a car when you can jump, read all the buses. You have to access to the same model of a working car, because also some UCU needs what we call a wake-up frame. If there is not a good frame on the CAN bus or some other bus, the ECU won't wake up, because a car has to be energy efficient, and when you park your car, you want it that it draw your battery in 1 or 2 days. That's why we decide to get to scrap Arduino and to scrap a whole car, and we gather all the ECU, all the wiring harness intact. So it's the best solution we had to avoid all the problem I listed before. Next, once you have all your ECU, you have to plug everything back. And honestly, it's the most difficult and the most time-consuming task. First of all, you have to find the documentation, the technical documentation, to know which pin on each ECU is used to be powered on, and which are the pin that act as a network, and so on. If you have quick tips, if you have a ECU with more than 20-30 pins, don't try to get its own connector, because you will waste a lot of time to find the good wire, because all the wire are almost the same color or same diameter. It will be quicker to plug directly to the pin into the ECU to get access to what you want. We also made what I will call a mistake. It's to keep all the wire as intact as it can be, because you lose a lot of time to untangle everything and clean everything, because you have a lot of grease and ink glue over all those things. If you don't find a ground on the pin of your ECU, it means that the body of your ECU is the ground. It's very common on safety ECU, like the airbag, for example. To illustrate what it's some work in progress while building the car in a box, you have on the left the wall harness untangle, which we waste many hours to get in shape, and then some progressing connectivity and identification and good wires to connect every ECU together. While you're having all your ECU on your hand, it's very important and useful to do a reconnaissance on all of this stuff. So you remove the body and look at all the PCB. It's very, very interesting. You can identify what chip are used, if it is a microcontroller or a system on chip, or maybe many of them. If you have access to EEPROM or flash chip, dump it, because in case of a wrong command, if you do the bad things, you can reflash it and avoid to break your car in a box. If you also can look at some debug access, like a GTAC port and some software debug ports. They are not so common, but it's always useful to get access to it, to know where they are. And then once you know the chip you have, you can look for documentation and have a very good knowledge of everything for the future path, if we want to reverse some firmware and so on. Then you have all your ECU, you connect them together, and the next step, you want to have a bench test which work like a real car. So you want to emulate the sensor. And on a car, you have 4 kinds of sensor. The most common one, the most easy to emulate, is a simple relay to ground or relay to plus 12 volts. So it's quite easy. If you have voltage on the wire, it's mean a 1, and if you drop to 0 or the inverse, it's mean a 0. And then you have a lot of sensor which act like which need a variable resistance, like a potentiometer. For example, the accelerator pedal or brake pedal, the more you push through, the more resistance it will have. So, well, you have to simulate this. And then you have 2 more signal you can have in a car. You have square signal, like the green signal you have on the right. For example, you will have it on the motor for the crankshaft or things like that to get, or in the wheel to get the speed of your car. And not so common, but quite complicated to emulate is our wave signal. Sometimes you can emulate a square signal to get the same effect like a wave signal, but not also. And how did we emulate all the sensor? For relay to ground, it's quite easy. We used an Arduino Mega because it has a lot of input-output on it. To emulate relay to ground or relay to run, we just connect to a pin and set it to run or not to get the results. For variable resistance, we use digital potentiometer, and so we can adjust using a digital value the impedance, the resistance we want to have the good signal. And for square signal, using the PWM, the onboard PWM of Arduino is not accurate enough. So we did we use assembly code from the microcontroller of the Arduino to generate a very quick and precise clock signal and add square signals. You alter up and down, and you get it. Quick tip if you want to do the same thing: having access to a diagnostic software when you can read the value of each sensor is very useful. So you can tune the good output of your microcontroller and add the result you want. Also, some critical sensor or actuators, like the one for the airbag, need 2 ohm resistor as a proof of life. Otherwise, if you don't have this resistance on them, you will have a default on your car and it will not work as you want. All sensors are not wired. Some sensors are using radio frequency signals, for example, like the TPMS, the tire pressure monitoring systems. So we also emulate all those sensors. We used software-defined radio system, yardstick one, and we record a signal from working tire pressure TPMS, and we craft the fake signal we want. And so we have a fully working system. Using this adding this SDR device, into the car in a box allows also more feature, like we can now replay or record key fob interaction. When you press your key fob to lock or unlock the car, we can record it and replay it, and we can demonstrate how remote keyless entry works, and for example, rolling codes are implemented to avoid thieves, to avoid that a thief steal your car. And then the last things, you have a working car, but you want to, it has to be used as the looking for my word. You have to use it for your training, so you have to interact with it quite easily and to demonstrate things. So we built a command and control system based on a Raspberry Pi, which has its own UI. There is a touchscreen on the car in a box, and the Raspberry Pi communicates through a serial communication with the Arduino. And with this, we can read the real value, like which is the speed that is simulated through the sensors, or what is the status of some error or are the lights turned on and off. So you can check everything and trigger a lot of things, not everything, but you can trigger a lot of things on the car, like you can see on the pictures. And as it is a Raspberry Pi, it has IP communication, so we can control on or broadcast the screen remotely, which is very useful for trainings. So to get to the end of this presentation, what experience we earn of building the car in a box. First of all, there's some things that we find very, very interesting, that ECU are not dedicated to one model of car. You will find the same kind of ECU between different models of the same brand, the same manufacturer, or you can find the same ECU share between different manufacturers. That's very important, because that means if you find a vulnerability into a ECU, it can affect a very, very wide range of cars. Another lesson learned is that not all sensors are real-time. For example, the fuel level made an average of every values it's read in a minute. So if you try to spoof or fuse the data associated to the fuel level, you will not find, you will not see a result directly. You have to wait a little bit. So be patient if you want to build your own test bench, own kind of box. On a security point of view, most of the microcontroller or system of chip have a read protection to avoid to dump the firmware. It was not designed to protect against malicious people, but mostly to deceive chip tunings, which is something car manufacturer want to avoid. Now for us at Quarkslab, building a basic benchmark for an audit is now very, very easy, because when you connect so many ECU, just connecting one or two together is quite easy. And the last thing is, if you have access, if you want to get into a car, having access to third-party diagnostic application is very useful, because you can have some information about the ID and the CAN bus or manufacturer command that were hidden, and you can work with those commands and see if there is something you can leverage to have specific interaction or access. And parties, if you want to, the car in a box was used multiple times. We did different internal hackathon at Quarkslab. When we play with it, we can learn to teach basis on car hacking. And you will also see it at the next hardwear.io USA 2022 in June at Santa Clara, if you want to have fun, to learn car hacking, to play with the car in a box, new connected NC and so on. So I hope you enjoyed this presentation, and if you have any questions, feel free to ask.
Thank you very much for the presentation. We actually do have 2 questions already, and while we are answering them, I would encourage others to write their questions if they have some. So the first question is, I have tried using the ECUS EM. Is there any alternatives available?
Well, ECUS-CM, ICSIM for instrument cluster simulation is a very good basis to understand how a canvas works, but it's very limited, because you think you will trigger the light, but you will only trigger the information on the dashboard that the lights are on, not the real lights. There is some, I think, get a look at the Car Hacking Village. They did very good stuff, and I know they did a VR game when you have some car hacking stuff, and you have some fork or ICSIM which are a little bit realistic, but not as realistic as a car or as a TinyECU.
Thank you. Another question is, there is no mention of OpenXCP port. Is this not considered part of the attack surface?
OpenXCP is a protocol; it's not a port at all. So you can have you have access to OpenXCP through the CAN bus and other things like that. So yeah, I was wider when I speak about attack surface.
All right. Another question is, how long did it take to build the box?
Many weeks. It took me 2 days to scrub the car, because I want to keep every ECU and wire harness as intact as it could be. And then as I said, I made many mistakes because it was my first big test bench. So all the recommendation I gave you could help you gain some time, but between 3 to 4 weeks to build all together, including all software and so on.
All right. Yes, this was another question. Another person asked the same question. How long did it take? But there's another question. And how much did it cost?
Well, go to eBay or some website like that and look for the price of the ECU you need. If you want to have something very cool to work with, I would recommend to have access to an infotainment unit, because you will have most of the interesting communication attack surface with it, like Bluetooth, Wi-Fi, if there are, or something like that. An infotainment used infotainment unit could be between €200 or $1 to much more, but yeah, it depends. And if you have a good friend like mine, we break its car, it will be cheaper.
Thank you. And I see one last question. Does any of the ECUs support UDS protocol?
All the ECUs support UDS protocol because it's mandatory. All car, when I spoke about the regulation, for environmental needs and for maintenance, all ECU needs to be need to have access to a diagnostic system. So you will find UDS in almost every modern car.
All right. A few other questions came in. Is it possible to purchase a car in the box as a whole unit?
Some company build not a car in a box, but big test bench to teach to workshop, to garage how to work with the car. So it's quite expensive. It's between, I think I saw some between 5,000 and 6,000 euros. But it's designed to be into a workshop, so you can travel with it. It's very, very big. But you have a real 12-volt batteries. You have all the parts of a car, and so mechanics student can learn how to perform diagnostics, use diagnostic tools with it. But it's not a cheap solution.
All right. Can you recover firmware in ECU if some damages breaks it during the pen test?
Yeah, as I said, if you have access to the ECU before playing with it, try to get the firmware first. So if you did something bad, you can reflash it. But to reflash it or to dump it, you sometimes need specific hardware, because as I said, microcontroller used in ECU are very specific. Thumbs are dedicated to some kind of embedded device for automotive or some specific industry, and you will not always find the correct documentation, or as I said, most of the time there will be a read protection in place. For Renesas microcontroller, for example, you will need to get their proprietary hardware interface to get to it. So that's not something that's quite useful, easy to get at. Sorry, and sometimes you can also look at manufacturer websites to find if there is some firmware update available. You can download and hope that they are not encrypted. For infotainment unit, for example, they are mostly. It's very common now that they are encrypted. And last idea I have about it, it's if you dig into the internet, you may find some websites when you can have a lot of dump of firmware available for a few bucks.
Thank you. And let's take one last question. How gross was the car you stripped to create the car in the box?
It's badly. He had accidents. It was not running anymore. All the ECU were intact, but all the airbag were on and stuff like that, and the car body was pretty bad.
All right. Thank you very much for answering the questions and also for the presentation. Guys, if you like today's session and would like to learn more about automotive security, Philippe will deliver a training, as he said, at hardwear.io USA in the first week of June. And his training will not only cover the theoretical parts, but also there will be a lot of practice. So if you'd like that, just check it out on our website. And also don't forget to fill in the feedback form because it also helps us to improve ourselves. And thank you for attending and hope to see you next time. Have a nice afternoon.
Thank
Bye-bye.
you. Soon.